So let's check out the practice homework. And the first one, a flea in flight. And just looking at the problem, you had a flea jumping straight up. So everything in the y direction. So going to jump straight up and going to come down. Important thing to know here, velocity, we use a standard coordinate system. Velocity is positive going up, but getting smaller and smaller. And then it becomes negative going down. And then getting larger and larger. Right at the top, at the maximum height, so max height, this is where the final velocity would be 0. So if we consider the start to be initial and the top to be final, then maximum height occurs when the final velocity is 0. So if we look at the information we have, free fall, so that means our acceleration is going to be minus 9.8. And if we look at what the flea jumps straight up with a maximum height, so we'll use y for up and down, and 0.41. They want to know what is its initial velocity. And we also have the final velocity is 0 at maximum height. And equation we can use here to figure out the initial is the v final squared. And plug our stuff in. And move that all to the left. So 2 times 9.8, 19.6. And we'll take the square root of both sides. .83. Let's check out the part B. How long is the flea in the air from the time it jumps to the time it hits the ground? So now, same picture, flea's jumping up, lands down. Now in physics, with vectors, we use displacement. So the flea, remember, I'm giving some separation just to try to show what's happening, but it's really just jumping straight up and down. And so the flea will start here and also end here, because it just jumps straight up, comes down. And if we're looking then for that displacement then is 0. We're saying the flea started from A, jumped up, came back down, landed at the same point. So its total displacement in the y direction is 0. Now this is different than the distance traveled. So the distance traveled would be how high the flea goes, and then plus how far it comes back down. That would be the distance traveled. But we use displacement instead. And that's just from the vectors. Vectors are always, if you have some point from A to B, no matter how we travel that, the vector always is from beginning to end, points right to it. That's what the displacement vector does. That's the same thing we're doing here. We also know acceleration is minus 9.8. And we have an initial velocity from the last problem. And if we want to know how long it's in the air, a good kinematic equation to use and plug our stuff in. And we'll divide everything by t. And put this over here. And divide both sides by minus 4.9. .58 total time in the air. So jumped straight up, came down, landed on the ground, total time in the air. And two important things there, that maximum height is when the final velocity is 0. And if you jump up and land back in the same place, then your total displacement is 0. And remember, that's different than distance traveled. Check out the next one. Got a lot of busy work there and more busy stuff. Let's just go right to the problem and see what it says. So we have a building 40 meters high. And I guess I do have to read somewhere here. Looks like we're throwing a ball up at 15 meters per second, going to some max height, and falling all the way down. But this is what they're working out here. And so I'm trying to look to see if they want us to just, throw it off the edge, kind of like that, or are we giving it some angle that throws it up into the air like this? Because this problem right here does show that they're throwing it straight up. And I just want to know if we're supposed to use this 15 meters per second here. Is that what we're supposed to use? So I'm going to go with that is. It's not quite clear that's what we're supposed to use, but I'm going to use this 15 meters per second as our, so we're going to have this type of trajectory going straight up, coming down. An initial velocity, 15 meters per second. It's in free fall, so acceleration due to gravity minus 9.8. The ball's going to start here, and it's going to end down here. So it's going to go from A to B. The displacement then is just that, from A to B, straight down. And because we're going to use a standard coordinate system, means this is negative. So the y displacement here is minus 40. And they want to know how long does it take to hit the ground. And we can use plug our stuff in. So I am surprised that we are going to have to use the quadratic formula already for the second one. Usually that's towards the end, but this is what we have. This is a standard quadratic formula. Where we identify A, B, and C. So, the quadratic formula, negative B plus or minus square root B squared minus 4A times C all over 2 times A. And I'll pause for a second and type all that in my calculator. All right, so remember the quadratic formula gives us two solutions. We reject the one that is negative time and take the one that is positive time, since we want what happens forward in time, not what happened backward in time. So there we go, 4.78. And I'm a little surprised by that. Normally, the having to use the full quadratic formula like that is not something that happens too often. Usually, they're a little kinder with their numbers they give to us. Let's check out part B. What velocity is the ball traveling at when it hits the ground? So we still have all our information here. And now we have a time value. So we've got 4 out of the 5 kinematic variables. So we can pretty much use all the equations here. But the easiest one, we want to know the final. And the initial was 15. So the ball is coming towards the ground. So we'd expect a negative velocity. And that is number 2. So here we have a brick is just dropped. So dropped initial speed, no initial speed from the roof, and strikes the ground in 1.5 seconds. It's free fall, so we know acceleration is minus 9.8. Because the brick is just being dropped, means our initial velocity time is 0, so we're not throwing it up, we're not throwing it down, we're just reaching our hand out there and dropping it. And they want to know how tall is the building. So looking for the displacement here. And we can get that. And 0 for initial velocity. So that'll just be 0 there. So the brick fell, standard coordinate, so down is negative, fell, minus 11 meters. But, they are asking for how high the building is. But let's see what happens if I do plug in a minus 11. So they want positive 11 for the height of the building. But what happens if I hit minus 11? They're not going to say anything. They're just going to say that's wrong. So say it's positive. There we go. Would have been nice if they gave at least a little hint there to be, your number's close. Just a sign error. That would have been nice. So just something to think about when Mastering Physics says you're wrong, that it may be something simple just like that. It was just a sign difference. So part B, how fast right before it hits the ground. So now we want to know what the final velocity is. We got all this information and choose one of the kinematic equations. We can go with this one. And our time was 1.5. And our initial velocity was 0. We just dropped it. And it is going down when it lands. We expect a negative value for going down. And here again, I'm going to put positive in, see what it says. And well, well, it took it that time. That's surprising. Even accepts it as positive. Okay. That technically should be negative, though. It is going down, which we do consider the negative direction in a standard coordinate system. Let's check out the next one. So measuring G on another planet. Take an object, fall a given distance, something we would have to measure. So they measured, so on some planet, want to measure the acceleration due to gravity. You could stand at some height. So they're standing at some height, 12.04 meters above the ground. They just drop some object. So just like the last problem, they're just going to drop it and use a stopwatch or something to measure that time. And so here, now this is still free fall because the only acceleration is due to gravity, but now due to some other planet's gravity. So that's actually what we're looking for here. And we are dropping it from rest. We're not throwing it. Whoops. So that means initial. Means our initial is 0. Just going to drop it. And our displacement here is going down. So it's going to be negative. And we want to solve for acceleration. So 0 times whatever there is going to be 0. Solving for A. So that's what I'll be punching in my calculator. And we're assuming if you jump up and you don't, the the planet doesn't push you away. So that's an acceleration coming towards the ground, negative. That's what you expect. And, oh, did I press wrong button? Well, I can't see what's wrong here, and I'm going to take a guess and say my math lab, mastering physics, I should say, is not using the minus sign. And I can't believe that is correct. Well, definitely something I'm going to send them some notes on here. This acceleration value should absolutely be negative coming towards the ground. Very, very unfortunate. There's not even any hint to say that maybe change the sign. But let's check out the next one. All right, so now they want it in terms of g. So we have this acceleration, 3.05. We've got g. We want to know how many g's this is. So in other words, some number times this 3.05. We want to equal 9.8. Well, I actually expressed this wrong. My brain is still broken. That mastering physics didn't take a minus sign there. Still bothering me. So what they want to know is how many, this g, this acceleration we have due to gravity on this planet, they want to know how many g's this is. How many of these g's, where g is 9.8, that on Earth. So this is actually what we want to set up and solve. So we'll do 3.05 divided by 9.8. So only a third of Earth's gravitational field. And see what they got for part C. How fast is the ball moving just as it lands? So going back to the information we have a time that's in the air, initial velocity. We also have displacement. We now have an acceleration, which should be negative. Otherwise, our kinematic equations won't work right. And we can use all that to solve for final velocity. I guess I'll just write it up here. The easiest equation to use would be this one. And just plug our stuff in with the minus sign. And our initial is 0. And I guess here goes another scary test. I'm going to put the minus sign in because that's what it should have. It doesn't take it. Well, they'll definitely get an email from me. And there it is. So remember, if anything's quirky, you can always send me an email and I'll fix whatever. Check out the next one. So we got another rock thrown vertically upward at 12 meters per second. That is 60 meters high. And they want to know how many seconds before it hits the ground. So how long is this rock in the air? And so what information we got? We got initial, positive up 12, acceleration due to gravity's minus 9.8. our displacement, we start here, we end here. That's down in a negative direction. So we're going to have minus 60 for our displacement. And that is what we know. They want us to figure out time. This is always a good equation to get time with. And we're going to get, surprising to me, another quadratic. And there's going to be A, B, C, T equals negative B. B squared minus 4A C all over 2A. I'm going to pause and punch that in my calculator. All right, so again, the quadratic will give us a plus and minus solution. We want the plus solution, the one that's forward in time, not the one that's back in time. And part B, what is the speed just as it hits the ground? So now we got time. We still have all this other information. And the easy one here to use is the linear equation here. And our initial was 12. And just because I'm really curious, this velocity going down. So this velocity going down, that's a negative velocity. You can see the math gives us the negative number. What if I put in positive and it takes it? And that's that one. All right, so here we have a relative velocity problem. And we've got, suppose you are driving north at 83 kilometers per hour. So maybe we're in Canada. So I'll put V us. We're 83. And a truck approaches in the other lane. Fortunately. All right. So just going by their picture, they kind of have us going up at 83. They have the truck coming down at 109. This is going down. We'd call that minus 109 in a standard coordinate system. And let's see questions we got. Suppose you and a truck are both traveling in the northbound lane. All right. So they changed up that initial picture, and they worked through that initial picture in this light blue area if you want to check that out. But so we got a different setup. We're same speeds. We're going 83. Truck going 109. It's passing us. And if we put a coordinate system on our car, So imagine that's our car. So if we put a coordinate system on our car, how fast is the truck moving in that coordinate system? So now our coordinate system is moving at 83 kilometers per hour. And so what we'll measure in that coordinate system then is this difference. I don't know why I can't. There you go. I kept hitting the wrong buttons. And part B, what is your velocity with respect to the truck? So, same picture. We're going north, 83. So is the truck at 109. But now they're saying the coordinate system is on the truck, is what they're saying. So now the coordinate system is moving at 109 kilometers north. And so still the same difference. 109 minus 83 is still 26. But in this coordinate system, try to imagine if you're sitting on this truck while it's moving and you had no other reference to look at, like buildings and trees and stuff, it would look like the car is just moving backwards to you at minus 26. So that would be if we put the coordinate system on the truck this time. And the minus better be on this one. I'm so stuck on this minus sign. What if I put positive here? All right, it doesn't take it. Well, that's good this time. And there we go. So another relative velocity. Driving eastbound. 60 miles per hour. And we're approaching a truck in your lane. A relative speed of 20. All right, well, let me just say I'm a little concerned here. We'll see what happens. The issue being here in this sentence, you observe that you are approaching a truck. So that means you're catching up to the truck. Truck's getting closer to you. It's not moving farther away, yet they're giving us a positive relative velocity, which suggests the truck is moving away. So I'm going to take their wording that the truck is actually approaching us, which is going to mean we're going to, so here's the truck, put the coordinate system on our car, traveling 60 miles per hour. If we're approaching the truck and we see a 20 mile per hour difference and it's approaching us, then the truck is minus 20 coming towards us in our coordinate system on the car. And if this is the case, then the truck must be traveling 40 miles per hour. And that is what they wanted. So, man, really having a tough time with minus signs here in mastering physics. Definitely going to get an email from me that absolutely should have a minus sign there. I think that is confusing. So we got the truck, we're instead traveling at the speed in the westbound lane. All right. So now our car going this way at 60, truck going this way at 40. And they want to know the relative velocity between you. So that means we're putting a coordinate system on our car again. Our car, which is traveling 60 this way. If as we stand on our coordinate system. We measure the car going this way then at minus 40 in our coordinate system. Well, from Earth, I should say there. Well, actually coming at us at 40, we'd actually measure minus 100 altogether there. So we're moving 60 this way. Car coming at us 40. We're going to have 100. It's going to be F. So imagine you're standing still, but you're actually going 60. Car coming 40. It's going to look like it's coming at us at minus 100. And I'm absolutely stuck on this minus sign. I'm not going to use it. Let's see what it says. And it took it. Let's try the next one. Jetliner has a cruising speed 620 miles per hour there. So we want to know how long does it take to make a round trip between two places. So San Francisco, Chicago, going there. $2,000 miles. There's no wind blowing. So no wind. So we're going 620 this way, 620 this way for a total of 4,000 miles. That would be our displacement, or distance traveled actually here. So our displacement here is this. And if we flip it around, got another 2,000. Our velocity being 620. And we can figure out the time. So this is the only equation that's left when there's no acceleration from this one. When acceleration is 0, that whole thing goes away. We're just left with x equals velocity times time. And that is in hours. So part B will probably have some wind here. Same round trip, same distance. The wind is blowing from west to east. So that's the way the wind's blowing. 130. And our plane does 620. So relative to the Earth, put our coordinate system there, we would see this plane going then 750 as it goes from A to B. And that was 2,000 miles there. So now we have 2,000 miles equals 750t. And that's for going to Chicago, and then from Chicago back, because we still have the wind blowing, so we're going 620 back, but the wind is blowing at 130. So standing on Earth, put our coordinate system, this will look like 490 to us as a speed. And same distance, 2,000. And add those two times together to get the round trip time. So the wind may help us get there from San Francisco to Chicago quicker, but then the wind works against us going the other way, making it overall 0.2 hours longer. All right, looks like back to vertical motion. Not quite sure how that got mixed up, but vertical motion here, a rocket initially at rest on the ground. Initially at rest. So now they're telling us the net acceleration here. So now I see this isn't technically free fall anymore because they're telling us what the acceleration is this time. So it's not the acceleration due to gravity. It's the acceleration due to the rocket thrust. And they're telling us how long the engines are fired for, 7 seconds. And then the rocket goes in free fall, meaning the only acceleration is due to Earth's gravity. So they want us to find the maximum height reached by the rocket. And all right, so we can have 2 stages here. We're going to have the rocket going up while it's accelerating. And that's for 7 seconds. And then it stops accelerating. And then it's going to be in free fall where the acceleration is minus 9.8. So there's a point here where the engines shut off. And we want to figure out first, what is this height where the engines shut off? And remember, the initial velocity is 0 here. And so we can use this equation to get that height. The acceleration is that from the rocket, fired for 7 seconds. And the initial velocity is 0, so this will give us the height. So that's what the engine's on. And let's figure out how far it goes once the engines are off. And what we're going to need here that's going to help us is to figure out what the final velocity here is when the engines turn off. And then this will become our initial velocity when the engines turn off. Well, let me say that again. We want the final velocity just as the engines turn off, so just as we reach 7 seconds. And then the engines shut off, and that final velocity will become our initial velocity while we're in free fall. So I want to find the final velocity with the acceleration of the rocket and a time of 7 seconds. So this becomes our initial velocity then when we go into free fall. And in free fall means we have an acceleration due to gravity. And at the maximum height, our final velocity will be 0. So remember, at the maximum height when something gets right there, that is a 0 velocity at maximum height. And we want to figure out what that is. And then we can use this equation where final velocity is 0. We know the initial minus 9.8 for being in free fall. And then we can figure out y. And let me move to over here. So 2 times 9.8 is 19.6. It's minus. I'll move it to the left to make that a plus 19.6 y equals 377.3 squared. And so I'll divide both sides by 19.6. So the rocket, with a height of 71,000 when the engines were on, and then when the engines turned off, it went another 7,000 up. So I'm going to add these two together to get the total height the rocket achieved. Well, let me check some numbers quick. All right, so this one I must have punched in a number somewhere bad. It's right here. Actually, when I type this number in my calculator again, I get something completely different. I actually get 1321. So big calculator error right here. Must have had a fat thumb or something. So here's the height while the engines are on. And then this over here is the height when it's off. So I'm adding these two together. Engines off and engines on. I'll add that. To get 8584. There we go. So a helicopter, 7 meters above the ground, descending, so descending meaning a minus velocity, drops a package from rest relative to the helicopter. So the package is not thrown from the helicopter, it's just dropped from the helicopter, but the helicopter is descending here. We have chosen positive direction to be upward. Package falls freely. So here is our picture. We got our helicopter. It's just this flying box, and it's descending. So it's going down with a initial, well, it's a constant velocity here because they don't say there's any acceleration. They just say it's descending at minus 3.7. So constant velocity of descent. And it is 7.1 meters above the ground while it's doing this and dropping the package. So the package is just going to fall straight down, but it has an initial velocity of minus 3.7. So it is dropped from rest out of the helicopter, but the helicopter is moving down. Also, the displacement here is minus 7.1 since we are going down in a standard coordinate system. Acceleration due to gravity, all negative numbers here. And they want to know, just as it hits the ground, find the y component of the package. The y component. Okay, that is usually when they say y component, that means there's an x component as well. That better not be. I don't see that it's moving forward. So they just want to know, what is this final velocity when it hits the ground? And we can use this kinematic equation, plug our stuff in. Want to know the final velocity. That's a minus 7.1 I'm squeezing in there. So that is because this is velocity squared, so we do have to take the square root to get final velocity. And square root has a plus or minus solution. The velocity is going down. Should be technically negative. All right, so I didn't catch the last wording here. They're being pretty tricky with this one. So this is the velocity relative to the Earth that I'm figuring out here, but it does say the relative to the helicopter. So we have our package hitting the ground at minus 12.4, going down into right as it hits the ground. But the helicopter is also going down at minus 3.7. So we do need to take this difference, or we're going to put the coordinate system on the helicopter now. So 8.7 is the difference in speeds here. The package is getting farther away from the helicopter. After all, it hit the ground first. So from the helicopter's perspective, this would be a positive velocity. And they still don't like that. And they want minus. All right, so actually, upon some thought here, I will accept the minus sign there. I will say that is correct. So just to clarify, we have our package, our standard coordinate system. So the package is getting farther away, but this velocity is pointed in the negative direction of our standard coordinate system. So I would support that actually being negative on that one. So again, the velocity of the package is going down from the helicopter, down being a negative direction. So part B, just as it hits the ground, find the component of velocity of the helicopter relative to the package. All right, well, I suppose that's interesting after doing the last one. So now, I guess we'll draw another picture here. Now the coordinate system's going to be on the package. Here's our helicopter going down at minus 3.7. Our package was going down at minus 12.4. So again, we have the same difference of 8.7. Same difference. But where the package is getting farther away. And sometimes this can be hard to imagine, but imagine you are the package. And as you look at if you think you're standing still, you're going to see the helicopter kind of moving away from you if you think you're standing still as the package. It's going to be moving away. And moving away in a standard coordinate system will be up, positive. So in this case, we would get the positive 8.7. So it looks like the helicopter is moving 8.7 away from us if we were the package, the coordinate system on the package. So we'll check out the last one. Oh, the Leaning Tower of Pisa. So as legend goes, Galileo dropped stuff off to test acceleration due to gravity. As is joked about in academia a lot, though, is he probably didn't do it himself, but probably had a graduate student do it. So let's check this out. A coin is released. So released normally implies you're just dropping it at an initial velocity of 0. Dropping it so it's free fall, minus 9.8. .41 meters above the ground. So we're going to go from here to here. In a standard coordinate system, that means negative displacement. So we're going to take this as a minus, don't know why I put a decimal place there, minus 41. And how much time is required to hit the ground? So again, the common one to use here is this kinematic equation. And initial velocity is 0, so there is our equation. And taking the square root does give us a plus or minus solution. We want the solution that's forward in time, so we'll take the positive solution. And what is the velocity just before it hits the ground? So right here, just before it hits the ground. A couple equations we could use. And we can use the same information again, actually, with this equation. So looking for final velocity, initial is 0. And we do have to take the square root of both sides in order to get just final velocity. So the square root does give us a plus and minus solution. The velocity of impact is going down in the negative direction. So in this case, from the square root, we would choose the negative solution since velocity is going down. And there is the practice homework. I have to say the minus signs was unexpected. And I just want to say again, if you feel things are quirky, you can always send me an email and I can check it out and easily at least change your answers. Not as easy for me to change what they accept as a solution, though. That's something I have to send an email about. So again, if anything's quirky, I understand perfectly. So just send me an email and I can take care of it. See you in lab.